The same way like what earlier we discussed, no, the moment of ions, moment of majority carriers. Similarly, what happened? We have to give explanation here. This is that. Oh. What do you mean by forward bias? The first one, the topic is when you connect the positive terminal of the P type, no, this is the P type, N type, and there's the electric field. That E you don't forget, showing that E. P type connected to positive terminal of a cell and N type connected to negative terminal. Now, what will happen here? Let's see that. So earlier what happened? The most energetic holes, they were able to move. The most energetic electrons, they were able to cross on their own. Am I right? And similarly, the most energetic holes, they were able to cross on their own from P to N type. And the most energetic electron, they were able to cross on their own from N to P type. And that is what that diffusion current, no? And we shown like this. At diffusion. Whether you connect cell or not, say irrespective of whether you connect cell or not, there'll be minority carriers, and that minority carriers I do show with the green color one. This is what the I drift. Whether you connect, whether in the absence of cell, this is what happens. Now what will happen? I will connected a cell. So what this cell will do? It's a positive terminal, and all is a positive charge. So what it does? It will repel this positive charge. No? So along with the most energetic hole, what happen? Other hole, what happen? Will get a support because there's a positive charge, there's a positive terminal, and there's a positive charge. So this was not having sufficient. By the time it comes here, what happen? It was able to go like this and will be repelled back because it was not having sufficient. The moment I switch on this cell and as I start increasing EMF, then what will happen to here is like this: the holes which are not having sufficient energy to cross the depletion layer, they also start moving. Along with the most energetic majority carriers, the other majority carriers also start moving. The similar is there's a negative terminal, there's electron, negative charge. The most energetic electron is able to cross. The other electrons which were finding difficult, which were not having energy to cross or depletion, they'll get energy from this. A repulsive force is acted. It will say negative term said, okay, no problem, I'll help you. Go, come on, you move. So that's what happens for the electrons. So I'll give number 1. Majority carrier. What about 2? 2 are not most energetic majority carriers, but they'll get a support from home, from the cell. So they will also start moving. I think the all majority carriers I'll show by one red color. It'll be easy for us to do comparison. Next, the one which got support. Okay, this 2 what happened? It got support. Similarly, this one. I'm giving different colors so that we can easy for to you understand. So without this cell, what happened? The 2 cannot move, but because of cell, it got some energy. So now what will happen? Along with the most energetic majority carriers, the other majority carriers are also able to move. No? What will happen to minority carriers? What will happen to minority carriers? This negative terminal. So what it will do? Will attract this hole. So it wanted to move like this, but this negative terminal what happened? Will try to pull it away from depletion layer. Same thing here. The positive terminal, the electron wants to go like this. Because of this positive terminal, what happened? The electron, instead of moving like this, it will try to move here. So what happened to the number of minority carriers they're crossing the depletion layer will decrease. So as I increase the bias here, the minority carriers will decrease. Majority carriers, they're able to move easily. Along with the most energetic, the other majority carriers are able to flow. Now, how the moment of charge? Let's see that one. This electron, this we know cell. Go back to the our this one current density. This will give electrons, no? These electrons, they flow like this. There's an n type, and these electrons, they come here. So what this native terminal will do, shall I say, it will inject electrons into the n type. Then how many electrons that are like injected by the native terminal into the semiconductor, those many electrons should be pulled here. So what this positive terminal will do, it will pull valence electron from here. I'll just show one valence electron. What is dot? There's a valence electron. It will be pulled out. It will be pulled by this one. The moment it's pulled, once it comes here, it will become free electron, and we'll get like this. In books, they within 1-4-5 sentence, they have shown everything. That one they didn't go in detail because you find very difficult, because you refer any book, you don't get explanation. So what is this valence electron? So what this positive terminal will do, it will pull out valence electrons from the p type. Positive terminals pulls out valence electrons from p type and injects free electrons in n type. I think there's a very important part. There'll be injection of majority carriers will occur. Now this electron, valence electron is pulled, no? So in place of this valence electron, now what you get it? So I think this valence electron only has become free electron now. Now an hole is generated, no? An hole is generated. Now this hole, what it will do? It will pull out this valence electron. So now what will happen is, like, the valence electron will come here and the hole will be formed here. Now this hole, what it will do? Will pull out this valence electron. So altogether, oh, okay, sorry, it is like this. No, this is there here. Now this valence electron will come here. Oh, this one, this is a valence electron. No? Yeah. And now here what when the hole should move like this, no? So how do it is able to push it? Like this particular electron will happen will. Okay, I think we'll stop it here only. And now this most energetic hole, how it will move? That we have to put it. Okay, this electron. Now I'll come to this one. Let me start from here. This electron, when it crosses here, what will happen to this? It will be captured by the hole. We'll get a valence electron. So the hole which is present here will jump here. So now what happened here? We'll get a valence electron, let's assume, due to recombination. The hole which is present here will make a jump. Then what do we get? Here electron, here hole. The hole which is present here, what it do? It will pull out this valence electron. The hole, what happened here? Electron has come, and here hole will be there. So like that, what happened? How the moment of here the valence electron is moving, and the hole is moving like this. What about here? Here the electron itself, free electron. So there are many things are there. So here how the moment, here the hole will move like this, because this electron, when the moment it comes, it will undergo recombination, and this electron will not move as a free electron, it will move as a valence electron, will jump from hole to hole. The electron will go like this, and that electron, when it comes here, will be pulled by the positive terminal. Shaker, mute it. So this particular free electron, when it moves from N to P type, here open will move as a valence electron, or better say the hole will move like this. The electron, the moment valence electron comes, it will be pulled by the positive term. Like this, what happen? The flow of charge will take place here. Because I have to give the flow of charge first. I'll put once again. The electron will move from negative terminal, will be injected here. This negative terminal, so because of enough energy, they will cross over depletion layer. Here what will happen? It will be captured by hole. So it'll become valence electron. This hole will capture it. So now where the valence electron, it has come here and on. Now this hole, what it do, it will capture this. Now this hole will capture this. And this particular hole open will capture this. And this valence electron will be captured by, will pull by positive term. So like that what happen, how the moment of hole is there, the holes are moving like this, better say. I'll show it here. Free electrons, and these are the holes. And what are holes in the p-type majority case? How do they move? They move towards the depletion layer. Now what will happen to the drift current? Shall I say it will, as I keep on increase bias, it will decrease, no? And what will happen to majority carrier? Diffusion current will increase. So if I, for bias non-zero, what I see that high diffusion will be greater than high drift. Don't say no drift current will be there, but it will be less. Why it will be less? Because the positive terminal will repel, will attract these electrons, will not permit this to move. Okay, all this sequence statement. What's happening to width of depletion layer? The width of depletion layer will decrease here. Sir, how come width of depletion layer decreases? So this particular, okay, come for this one. How the width of depletion layer decreases means, if you look at this one, these electrons, or instead of moving, they can take this position. These electrons, so what will happen? Instead of crossing out depletion layer, they may come and take this position. So here electron, here electron. So what's happening to width of depletion? What is the depletion layer? Should not contain the free electrons and holes, no? So these electrons, some of them open, instead of crossing depletion, they'll occupy this position. So what's happening to width of depletion layer decreases. Similarly, the positive terminal of cell will pull valence electron. Because of that, the holes will move. These holes, when they're moving here, they may take this position. They may take this position, means this hole will pull valence electron from here. This hole which is there, no, will pull valence electron. So what actually phenomena occurs? This battery will pull this valence electron. This valence electron, what happen? Okay, this particular hole open will pull valence electron from here. So hole has come, and this valence electron will be pulled by this hole, and this valence electron will jump to here and will come like this. So what's happening here? The width of depletion layer decreases. So in forward bias, which current will be more? Diffusion current greater than drift. And what happened to width of depletion layer decreases. This is something very important. The width of depletion layer decreases. This is one thing. Then I diffusion greater than I drift. So what this forward bias now will permit the flow of majority carriers, no? Forward bias, it will permit more majority carriers to pass through it. Now let's see that covalent making and breaking of covalent will take place here. Here also now the covalent bond open will break up due to that minority carrier generated, due to the diffusion current will flow. As the width of depletion layer decreases, what happened to number of covalent bonds breaking up? That will decrease. So gradually the drift current will decrease here. Means now let's say that what is the barrier potential? We said 0.7 volt, no? And I applied here. So you do one thing, it's a similar idea like this. For 0.7, for minus 0.7, first I'll add 0.1 volt. How much it will become? 0.6. Net potential difference. For 0. Minus 0.7, if I add how much? 0.2. Net how much will become? Minus 0.6. So what's happening to barrier potential? You see that one? Earlier, without bias, it was like this. Look at now this one. Why minus n means this will oppose, no? For with respect to majority carrier, I'm writing a negative sign. So for minus 0.7, you add 0, minus 0.7. There's a barrier for majority carriers. Now, when you add plus 0, who is this 0.1 node? This cell. So as I keep on increase EMF, tell me what's happening to net barrier potential? Keeps on decreases. It keeps on decreases. And at one instant, what happened? No barrier potential. Sir, then what about this, sir? Can you write anything about this? How much it has become? Plus 0.1. No? Means what will happen? The depletion layer will, this will become positive charge layer, this will become negative charge layer, which is of no use. Huh? The diodes what we are using will not occur this. I'm just telling, it can even change polarity here when this occurs. During this situation, positive charge layer on N type, negative charge layer on P type. During this situation, negative charge layer on the N type and positive charge layer on P type, it can occur. When that will happen? When the bias voltage is more than the barrier potential. So what's happening, as you increase the bias here, the barrier potential decreases. As the barrier potential decreases, the opposition to the flow of majority carriers will decrease. So more majority carriers will pass through it. As the barrier potential decreases, number of covalent bonds breaking up in depletion decreases. The diff current decreases. So when I plot this forward bias, means so what this forward bias, in the forward bias, what shall I say, that the opposition to the flow of majority carrier decreases. So if I plot the graph, how the curve will take place, will take shape like this here. This is the forward current in milliampere, and there's the forward voltage. Somewhere you can see that there will be sharp rise is there. Afterwards, it starts rising sharply. I'll give suitable curve. It should be like this. After this, there's a sharp rise. This we'll call it as knee voltage. What do you mean by knee? I think when you look at your leg, so there's a sharp bend, no? Look at this curve also, similar to like this. So if you draw the leg, okay, it is, this curve is similar to knee, no? So this is called as a knee, am I right? This is called like a knee. This part is a knee, no? This one. This is called like a knee. This is called a toe, lap. This one. So this is a knee, no? So it is similar to like a the bent leg, no? This is, so therefore this is called like a knee voltage, where afterwards what happen, almost the barrier potential will vanish here. The diode is totally forward biased here. I'll take it out this. This is, I should not draw. There's a reason why they are calling that knee voltage. There's a 0 volt. Okay, now I'm more interested. This is for what is the knee voltage? Knee voltage, or is also called as a forward voltage. For how much it is? 0.7 for silicon. 0.3 or 0.4 for germanium. A few small things. What about in this region here? I diffusion is greater than I drift. What about here? I diffusion very much greater than I drift. Minority carriers will be there, but they're negligible. Almost it's negligible. We need not to bother that. Then you calculate the slope in this region. If you calculate the slope, so this is delta I, this delta V. So the reciprocal of slope is called as the forward resistance. This is 1 by slope here. So how much it is? Delta V by delta I by delta V. Nothing but equal to delta V by delta I. Where we have to calculate? We have to calculate forward resistance. This resistance by ohm. The resistance by the ohmic regions. because no longer depletion layer, no depletion, better you write it, no depletion layer here. Here, depletion layer thickness decreases in this region. Here, no depletion layer after this. So now, where we are calculating the resistance after new voltage, no depletion layer will exist. Then resistance by whom? By the P and N region. Resistance by the P and N regions. Because this material will offer resistance. No? When electron is moving, it will encounter collisions in this region. Will encounter collisions. So therefore, here what happens? We don't get any further like a depletion layer. So that's called a forward resistance of the diode. So here is what we are going to operate here. When we should, where we should use diode, this is called a operating region. We should use the diode in this region. So how the diode circuit, how do we show diode circuit? The symbol here afterwards, we don't go for like this. When we are doing problem, no, the diode will be shown like the symbol like this. This is the P type, N type, and this is connected to cell. And always there'll be one series resistor to protect the diode from exceeding voltage. This is cell. And so this is a symbol of diode. P type, this is N type. The base of a triangle will be P type, and this one line, this will be N type here. So how the forward bias current, because I have to show that IF, no, how to get the direction of current opposite to flow of electron. The direction of current should be opposite to flow of electrons are moving. So shall we put it opposite IF? So how the current will flow from P to N region. So inside here, how you have to show that IF? You have to show like this. Agree, no? This current is due to what? Due to only holes or only due to electrons? Due to both. This forward current. And the depletion layer, what happens? Thickness, width of depletion layer decreases, diffusion current will become greater than drift. Rest all everything you can carry on that one. What all I gave explanation. So this what happens in a forward bias. So now, so if you look at the some books here, the conventions, like when you take the diode when it is forward bias, no, what I should replace? Almost shall I say no resistance. If it is the ideal diode, we replace with a short circuit. The first approximations, I think I'll come to later on this one. Evening 1 hour I'll take it. So let me explain further. A few more things are there. Evening I'll do the reverse bias, then some numericals. Now look at the diode now. What is the resistance of diode? Resistance offered by P and N region. What is this forward bias once again? So this is the applied voltage. So you look at this particular point. Here what's happening? The depletion rate. So here now. So what is this? Says this 0.1 volt. But what is the barrier potential? Minus 0.7 volt. So the net barrier potential 0.6. So earlier here, some, let's assume 100 majority carriers were flowing. Here how many will be? More than 100, because slightly barrier potential decreased. Here how many will be? 300, 400, 500, 600. Almost here what happen? No barrier potential will come. So as we increase the bias here, so what happen to barrier potential will keep on decreases. You need to go for further in detail because this is enough explanation I give. Almost 2 hours I spent only to show that flow of charges. So now for numericals, what you have to do? Width of depletion decreases, for diffusion current is will be very much greater than drift current. Now, what is this forward current? The forward bias is due to diffusion current or drift current. What shall I put it? Due to diffusion current only, no? Both will be there, but diffusion current will be greater than drift current. And the forward current is due to majority carriers or minority carriers. The forward current is due to majority carriers. So these are some very important. What is IF? This IF is due to majority carriers or due to diffusion of majority carriers. Let me write here. So what all that forward current is due to? Diffusion of the majority carriers. There'll be drift current, but it'll be very, very small. That already I shown it here. And there's resistance offered by the P and N regions. Okay, this overall. Okay, let me just briefly summarize what actually happens. Because again, you take the SC Verma, they're also open like this moment of charges are not shown. Just they put one sentence here. Now, what shall we put here now? As you increase the bias, what happen along with the most energetic electrons, like energetic electron holes, along with one, what I numbered one, no? Those electron holes which are number two, they also start penetrating, they also start crossing through depletion layer. Fine. The thing. So now moment of majority carriers increase or decrease? As increase. Along with this, this will also, they will cross. Earlier 100 were crossing. Now open 150 will cross it. As you increase further bias 200. As you increase bias 300. Like that the major, like amount of majority carriers increases. This is the first thing. This one. Next again. What will happen to the flow of electron? The negative terminal will inject electrons. These electrons, what will happen? Like they have energy. So few of electrons will come and take this position. Clear all of you? I say I'm summarizing the most important part. They may ask you any theoretical question on this. The electrons injected by the cell, there'll be injection of majority carriers will occur. So these electrons open, few electrons will go and take this position. Next few electrons open, they have enough energy, they'll cross over depletion layer. This electron which has moved from N to P type, what will happen will be captured by hole. And it will jump from hole to hole. Then how hole is moving? Hole is moving towards right. This electron, now how this electron, here it will move in the form of valence electron. So nothing but hole is moving towards right. So I'm showing it here. Now this valence electron, the moment it comes here, will pulled by positive terminal and it become free electron because the free electron can flow in the wire. Will come like this. The moment of charge will occur. Sir, why don't you explain in terms of hole? Yes, I'll explain hole also. This I took electron, the hole. So here what happens? This positive terminal will pull the valence electron. Okay, got this. So here one hole is formed. So now this valence electron will jump here. So the hole will jump to this. Now the valence electron from here will jump. The hole will jump. And the valence electron from here will jump. The hole will come. And this hole is having sufficient energy. It will move like this. The hole which is moving here will be captured by the free electron. Then select a one hole and electron are lost. Is from where do it come? Breaking up of covalent bond. The covalent bond which will break up, the electron which is lost will come back here. And the hole which is here, no. So here what don't think the hole will move here. That you should never show hole here. The hole will become minority carrier. So what will happen to it now? It has to move like this. Clear this. And the electron which is coming here open will interact with hole and it will also be lost. So like that here, breaking and making up of covalent bond here. Breaking and making up of covalent bond. Here breaking and making up of covalent bond here also. But as the width of depletion layer decreases, tell me what happened to the number of covalent bond breaking will decrease. So I drift will decrease. And moreover, this whole open will be pulled by negative terminal. No? It will not permit easily to move through depletion layer. So therefore, the drift current will decrease by large amount. So without depletion layer decreases, and there'll be moment of charge. And finally, what happened? What is the resistance offered? Resistance offered by the material of the diode, by the P and N region. That is the forward resistance. So when you can say the diode is forward bias, it is in this region or this region. In this region, the diode is forward bias. Only in this region we can say that one. So here also what you have to write again, making and breaking up of covalent bond will occur in all regions. So I'll summarize what actually in forward bias. Last final. Increase in flow of majority carriers across the depletion layer or across the junction, better write it. There's the one thing. Next again, on this I need more points. No? I need more space. Some 4 points I'll summarize. These are the conceptual questions they may ask. What actually happens in forward bias? And there's an increase in flow of majority carriers across the junction. There's a 1 point. Then width of depletion layer. Width of depletion decreases. Here also making and breaking of covalent bond occurs in all regions. This is a very general thing. What will happen to drift current as the bias increases? Bias means as the EMF of cell increases, or applied bias we call like this. Applied bias increases. What will happen to the drift current? The diffusion current will become more than the drift here. These are the some very generalized things. So here also again recombination will be taking place. Due to recombination, what will happen? There will be photon generated. It will be generated, and also there'll be the moment of these electrons when they're moving in p and n regions, they'll encounter collisions and it will be generated. So there's a one overall idea of the basic the forward bias. Okay, evening I'll intimate the time. I'll talk with the chemistry sir, then I'll give the time. 1 hour only. We have to finish up the reverse bias theory also. Okay, thank you all of you. Any doubt? If you want, you can clarify, because I think a lot of things are being. Any doubt? If you have, you can clarify. I'll wait. Any doubt? If you have, you can clarify it.